Good morning to all of you. In previous session, we have seen IR filter designed by impulse invariant method, where we have seen three mapping functions. So we also used those three mapping functions in various examples to convert the given analog function into analog filter into digital filter. So in today's session, we'll be discussing IR filter designed by bilinear transformation. So in case of IR filter design by bilinear bilinear transformation. So again here we'll be using one mapping function, right, as we did in case of impulse invariant method, as well as in case of approximation of derivatives we used some mapping functions there, right. We also will be using a mapping function which has the form s is equals to 2 upon capital T in bracket 1 minus z inverse upon 1 plus z inverse, or this can also be written as 2 upon capital T z minus 1 upon z plus 1. Okay. So here we'll be using one frequency which is also called as resonant frequency. So the values of that resonant frequency has the form omega is equals to 2 tan inverse ohm t upon 2. So where this ohm value depends on the system function, that is nothing but h of s, right? Or even you can write the equation for ohm as 2 pi t, right, tan omega upon 2. You can indicate as omega or omega r, right? So this omega r is nothing but the resonant frequency. So let's try to solve some example here, right? We will be using this mapping function to convert h of s into h of z, or the given analog filter into the digital filter. Okay, so here you can see that the given system function, the given system function h of s is equals to, what is that, s plus 0.1 whole upon s plus 0.1 square plus 9. Okay, okay, so here the resonant frequency has been given, so omega r is equals to pi by 4 is specified. Even you can identify the value of ohm, right, as I have said in previous slide. It depends on the system function. So here the value of v is nothing but value of ohm. So value of ohm is 3 in this case, right? So from this you can identify, by using this equation you can identify the value of capital T, right? So just for example, if I'm using this equation, ohm is equals to, what is it, it is 2 upon T, 2 upon capital T tan omega r upon 2, right? So capital T can be written as 2 upon omega, right, tan omega r upon 2. Okay, so the value of T will be 2 upon this ohm is 3, right? So tan pi by 8 will be there, and if you evaluate it, so it will be 0.276. So this capital T is nothing but 0.276. Okay, so this is the required value, right? So again, this h of z can be obtained from h of s, right? So this h of z can be obtained from h of s by substituting s is equals to what? 2 by t z minus 1 upon z plus 1 in place of s, right? So where there is s, I will be substituting that value. So what I will get here, so in place of s plus 0.1 is there, right? So it will be 2 by t z minus 1 upon z plus 1 plus 0.1 is there, 0.1, right? Whole upon, again this s plus 0.1 square is there, so that means this 2 by t z minus 1 upon z plus 1 plus 0.1 whole square plus 9 is there, right? Okay, so again here in place of capital T I can substitute this value 0.276, right? And I can simplify it as to get the actual value of h of z. Before that I can again simplify h of z. So here this is 2 by t, right? And if I simplify the remaining equation, so it will be z minus 1 z plus 1, this z plus 1 goes into numerator, right? Plus 0.1 z plus 1 whole square will be there, will upon, because this 0.1 z plus 1 will get multiplied and this denominator z plus 1 will go into numerator. And again this 2 by t will be there, right? Again z minus 1 plus 0.1 z plus 1 whole square will be there, right? If I simplify these terms, plus 9 and this z plus 1 whole square will be 9 z plus 1 whole square will be there. Now since capital T is what we identify 0.276 s, if nothing is given in the example, then you can assume capital T is equals to 1 second. But here the resonant frequency was given, omega we identified from the equation, right? So therefore we can uh, replace this capital T with what we identified, that is 0.276. So if I'm substituting capital T value in the equation, so it will be simplified as 1 plus 0.027 z inverse minus 0.973 z to the power minus 2 whole upon 8.7, not 757, 57 minus 11.84 z inverse plus 8.177 z to the power minus 2. Okay, so this is the required system function for the digital filter. Let's solve one more example. Okay, so here in this example we have to apply bilinear transformation to get h of z from h of s, and capital T is 0.1 second given, right? So I'll directly write down h of z can be obtained from h of s by substituting s is equals to 2 by t z minus 1 upon z plus 1 in the equation, right? So it will be 2 upon this, in first bracket it will be 2 by t z minus 1 upon z plus 1 plus 1 will be there, right? Again 2 by t, again z minus 1 upon z plus 1 plus 3 is there, right? So here, as since this capital T is 0.1 seconds, right, I can substitute this value in the equation and I can have h of z is equals to 2 upon, so it is 0.1, 2 by 0.1, so it will be 20, right? Again z minus 1 upon z plus 1 plus 1, and again 20 z minus 1 upon z plus 1 plus 3 will be there, right? So again, if I multiply and simplify it, so I'll get this h of z. H of z is equals to, I have 2, this z plus 1 whole square will be there. It will go into the numerator, right? So 2z plus 1 whole square will be there, all upon this 20z minus 20 plus z plus 1 will be there, right? And 20z minus 20, 3z plus 3 will be there. So if I simplify it, or initially if I simply simplify these brackets, so it will be 20z minus 20, and it will be z plus 1, so it will be 21z 20 minus 20 plus 1 will be minus 19, right? So in bracket it will be 21z minus 19 in first bracket, and in second bracket it will be 20z minus 20 plus 3z plus 3. So minus 20 plus 3 minus 17 will be there, 20z plus z will be 3z will be 23z. Okay, so 23z minus 70 is there. Again, you can simplify it, okay, or you can keep it as it is, but as we know that we require that system function in z inverse form, so you should make certain adjustments so that you can get the z inverse there. So I will leave this for you to complete it, right? Okay, next example. Again, in this example you have to uh, identify h of z by applying bilinear transformation to the given system function, right? So in this system function, again, the bandwidth 0.25 pi has been given, right? So I will directly write down the solution here. I can use this ohm is equals to 2 by t tan omega r by 2, right? And the value of omega is given 0.25 pi, right? So if I substitute that value here, so it will be 2 by t tan 0.125 pi would be there, right? That is 0.25 pi by 2, right? And if I evaluate it, so it will be ohm is equals to 0.828 by capital T, right? Tan 0.125 pi multiplied by 2 will be 0.828. Again, by using this bilinear transformation, h of z can be identified from h of s by substituting s is equals to 2 by t z minus 1 upon z plus 1, okay, in place of s. So it will be equals to this ohm will be there, right? All upon place of s, it will be 2 by t z minus 1 all upon z plus 1 plus ohm will be there, right? And in place of this ohm, I can substitute 0.828 by t value, right? So I can have h of z is equals to 0.828 by capital T whole upon 2 by t, right? Z minus 1 z plus 1 plus 0.828 divided by t. So here this t will get cancelled, right? So if I'm cancelling all those t, right, and simplifying this equation, so I can get 0.828 multiplied by z plus 1 in numerator, right? So h of z is equals to 0.828 z plus 1 in numerator, and in denominator I will have then 2 in bracket z minus 1 plus 0.828 z plus 1 will be there, right? in bracket z minus 1 plus 0.828 z plus 1 there, right? Again, I can simplify it and I can modify this z inverse, right, to get h of z in z inverse form, right? So again, I'll keep it at your end. Try to write down the h of z in z inverse form, right? Whatever system functions that were seen while realization of IR systems, all those system function has terms of z in negative powers of z, right? So likewise, you can apply the bilinear transformation. Let's try to solve one more example here. Here again, the capital T has been provided from h of s. You can directly identify h of z by substituting in place of s value as 2 by t, z minus 1, z plus 1, right? So what you'll get, 1 upon this value will be there, that is 2 by t, and z minus 1 upon z plus 1, right? Plus 1 whole square will be there. In place of t, you can substitute 0.1, right? So h of z will be 1 upon 20 if I substitute 2 by 0.1, z minus 1, z plus 1 plus 1 whole square will be there, right? If I simplify it, so it will be h of z is equals to z plus 1 whole square in numerator will be there, then 20z minus 20 and z plus 1 will be there, so it will be 21z minus 19 whole square, right? So this is the required system function, but again you need this power of z should be negative, so again I will keep this as an assignment for you. So h of z is equals to what I have, last function, z plus 1 whole square upon 21z minus 19 whole square. Okay. So this is how you will be using bilinear transformation to get the digital filter from the given analog filter by converting its system function h of s into h of z by utilizing different mapping function. Okay, so here we use this mapping function, that is bilinear transformation mapping function. So that's all for today's session, and thank you for joining this session.